So we have Nelson Walker and Michelle Ouellette from the United States Air Force. They're both from the 812 Test and Support Squadron, is that correct? Out of Edwards Air Force Base? Correct. Okay, very good. And I will just go ahead and let you get started. Let me know if you want me to click on it. Well, let him know. He knows what's up.
Nelson is driving, so let him know.
All right, you ready, Nelson?
I'm ready.
Okay. So we have been doing some research out at the Global Reach Combined Task Force, the CTF. And so our presentation today is we're using Changepoint detection and artificial intelligence to classify fuel pressure behaviors in aerial refueling. And so I just want to make a comment real quick that none of this would be possible without some extensive collaboration with our engineering counterparts. They could not make it today because they are doing their engineering thing down in Florida, working with our SAG and NATO. So part of what made this possible. So Mr. Wellborn, Mr. Valois, and then one of our fellows from the 812, Mr. Bailey. So, so in general, for those of you not familiar, air refueling is the process of transferring aviation fuel between two aircraft during flight. So giant gas stations in the sky. You don't want them to collide. You don't want things to break. You don't want things to go outside of spec for anything. So there's two main systems with which to do that. There is the probe and drogue and the flying boom. So all of the data that we've used for our analyses and tool building so far has come from flying boom. Because it is a rigid structure, we can actually put sensors on it in different ways. And so we've got higher fidelity of data in the right places to be able to better match the evaluation criteria and things. So in general, this allows all of our troops to extend their range, increase their mission capabilities, accomplish different things. So for air refueling, our tankers have to supply fuel at a constant pressure to a receiver aircraft. And we have to take into account both safety and efficiency. So safety is important because pressure goes too high, things will break. Pressure goes too low, it will take too long to refuel, and that has serious mission impacts if they're out in theater. So the ATP or Allied Technical Publication 3345, it's a NATO publication. It contains all of our area refueling standards for fuel pressure. So all of the all of the evaluation criteria is based off of content contained there that is developed by our allies in conjunction with the Air Force. So in general, fuel pressure is highly stochastic. It can be affected by a variety of things, including things like flight condition, what maneuver is being conducted, and how the equipment is configured for things. So as you can see down below, we have a bit of noise there. That's actually a very well-behaving one. With what the noise that you see, it can get quite a bit noisier depending on what's going on for a particular thing. Slide. So in general, we've got a couple of things that feed into the evaluation criteria. So that includes the presence of oscillatory behavior, because again, we want that to be constant. So if things are oscillating, then that can cause problems. The number of nuisance disconnects, can the tanker and receivers stay connected for things? Are they only disconnecting when they're supposed to disconnect, or are they popping apart while they're trying to transfer fuel? And then the max fuel pressure for both steady state and transient behaviors. So that can change depending on what pairing is being used, because those numbers are dependent upon the particular aircraft. And so usually we are working off of whatever the smallest of the two is, that max fuel pressure. In general, our evaluation relies on calculating some metrics as well as traditional statistical inference. So like, for instance, how much time is spent in a particular type of state. So how much time are you oscillating? How much time are you in steady state? How much time are you having like transitory spikes above where you want to be for the fuel pressure range? We also want to try to do what is the expected maximum fuel pressure. So based off of the data that we collected, the variability that we saw, can we predict what a reasonable maximum might be, taking into account the variability that we saw here. Our metrics, though, depend upon accurately and consistently identifying where these fuel pressure behaviors begin and end. So as you can see down in the figures, so we have a little example segment. And then, for instance, one engineer might make one set of decisions, another might make another. So some of that depends entirely upon what have they been exposed to in previous pairings, how were they trained, who trained them. And so some of it is a little bit more subjective, and we're trying to take some of that subjectivity out of where we put in our decision-making points. So also manual fuel pressure classification tends to be very time intensive, and it's not necessarily reproducible between engineers in a very precise fashion, because again, it depends on their training. So all of our previous efforts so far to apply traditional statistical methods to try to classify things in a consistent, reproducible, defensible manner, they haven't really worked very well. They've been overly complicated. They have not functioned the way we'd like them to. So the main problem that we're faced with is really, when does that behavior start? When does it end? And then how do we correctly classify what is in those identified places? So can we consistently put the beginning and ending pieces in the right places? Once we've done that, can the system correctly and consistently identify it? What? So in general, too far.
Sorry.
So in general, we've kind of developed a large backlog. So they have used engineering judgment thus far so that they can do decision-making for things like, is this pairing safe, using what we've been able to do with engineering judgment, et cetera. However, we do have a large analysis backlog, which is around 30 different report packages. And so each report package is a different tanker and receiver pairing. And so we have multiple tankers. We've got a lot of receivers between all of these tankers. And each of these packages is expected, just for the fuel pressure analyses, to take about 280 man hours to meticulously go through all of their data for this. So that includes the engineering time and the time for analysis. And so you can see why we are in a backlog and we haven't gotten to them yet. So that's going to be roughly about 8,400 man hours for all of those. And we are continuing to evaluate more platforms as we go. So this list is bigger now than when we wrote this. So we are the Global Reach Combined Task Force. We are trying to wait to publish some of these things because we don't want to continuously put out data packages. We would like to be able to do all of the analyses that we need to fully report on things. And so we're trying to wait until we've developed some kind of classification system for this. So in general, we've had heavy collaboration between our statistical methods home office, our Global Reach engineering SMEs, and the data science section assigned to the Global Reach CTF to try to save this time, effort, and money. So we're basically investing in all of this time up front and developing the tools so that we can save significant man hours and go to work on these packages. So, and in general, it's been very interesting. We've had a lot of interest from all different CTF levels. So like all the way down from the individual engineers going, whoa, we can do that, up to leadership going, ooh, look at all the manpower and whatnot that we're saving for this. And so it's been very interesting seeing the different inputs and requests from different levels of interaction with our engineering counterparts. And for that, now I'm going to pass off to Nelson, where he will describe a lot of the nitty-gritty of how does this work and what have we done to develop it.
Thanks, Michelle. Can you guys hear me all right?
Yep.
Okay, perfect. So this whole, problem set that we're trying to work through, I guess there's a couple of different ways that we could address that. I think looking at some of the other talks that we saw, I mean, reinforcement learning or machine learning in some vein would be, a natural way to look at this problem. However, we don't really have answers to work with in the first place that we can hang our hat on, say, this is the authoritative, like what's going on in these fuel pressure data streams that we're looking at. So we come up with a solution that we call the Fuel Pressure Artificial Intelligence Classification System, or FACS. And it has a couple components that we're going to go through. The first is that we implemented a change point detection algorithm. And that is unsupervised because we don't know, like, I mean, first of all, we don't know what type of behavior we're looking at before we look at it. Like the subject matter experts did not provide us with answers to work from, and did not provide time hacks for where different behaviors start and stop. So we're going to be coming up with that information from scratch. So the goal of a lot of unsupervised machine learning algorithms is to divide observations into homogeneous groups that are often called clusters or segments without knowing what group they should be put into. We used a change point detection algorithm called the pruned exact linear time algorithm, and that identifies with a particular version that we use, it identifies when the mean and the variance of time series data changes in some way. We use the Changepoint package in R to be able to implement that. The underlying likelihood that was used as a cost function was the gamma likelihood. We used the BIC, Bayesian information criterion, as a penalty term. And then essentially how the algorithm works is it starts at, in the first observation of the data stream and goes from left to right, beginning to end. And it inserts change points that optimize the penalized cost function. And it's pruned because a number of different change point detection algorithms kind of evaluate the whole data stream and then pick out where change points should be inserted kind of one at a time, and this goes from left to right, so it makes things faster. So what we're seeing down here in the lower left is that same data stream that we've shown a number of slides before, and the blue vertical lines are where change points were inserted by the PELT algorithm. And then in the upper right, we blow up a section, or excuse me, the lower right of this slide, we blow up a section. You get a chance to see that in the left side of that area that's been blown up, we've got relatively steady behavior, and then all of a sudden the fuel pressure drops, right? And then it starts going up and down and up and down. So it's oscillating and it's spiking, and then it kind of settles down a little bit, and then it starts going nuts again. So like this algorithm is pretty effective at being able to identify those types of changes. And this, unfortunately, in and of itself is not enough to be able to really have something to work with in identifying different fuel pressure behaviors. This is this has to be reinterpreted in some way, right? To be able to say these different segments within or between change points should really be classified as a specific type of behavior. And that's where the second part comes in. We crafted an expert system to interpret those change points and then classify the segments among and between them. So this has been highly collaborative and very iterative, where we put heads together with subject matter experts to build out this expert system. And that's because expert systems are a type of AI that emulates the decision-making ability of an expert. And they kind of came into being in the 1970s and were used a lot in the 80s. And they were applied to a set of problems that kind of in our modern day have really been taken over by neural networks in terms of a solution. Like the really prominent ones, like trying to translate languages or trying to transcribe speech to text. Those, had limited success when these were first attempted as expert systems, and the cases where expert systems worked very, very well, like they've just kind of been integrated into life so much that you really don't acknowledge them as much as an expert system anymore because they're just very common. But an expert system, kind of at its basic, and at least how we implemented it, is a rules-based set of logic that's used to classify fuel pressure behavior based on one or more adjacent segments of an overall time series stream. And the rules that we program and pick are based on evaluation criteria that's relevant for the engineering staff, definitions of various states that have to be kind of well-defined and programmed in, and in some cases tweaked, as well as statistical properties like the mean, maximum, minimum, and left-right edge values of any given segment of fuel pressure data, as well as the shape of what's going on within a segment. Is it like a, is it a maximum, a minimum? Is it overall going up or going down? That kind of thing. So there were a number of different types of behavior that we identified through subject matter expert collaboration that we need to be able to pick out and identify. In the lower right, you see a couple of different behaviors that are grouped together and then color-coded. So you've got the green is what we call steady state behavior, where things aren't changing very much. The changes are below a certain threshold. The yellow is kind of a conglomeration of all kinds of different types of transitory behavior where there's spikes or oscillations. And then the gray is like, it's not really steady state, it's not really like transitory. So, it's not bad enough, or it's not variable enough to be called transitory, but it's not quite meeting the characteristics of steady state either. So an example definition of an oscillation that might compose this type of behavior that you see in yellow is we want to identify segments where the range in fuel pressure between troughs and crests is greater than X pounds per square inch gauge, and that range doesn't drop below Y pounds per square inch range of difference for at least Z cycles. And we separately classify oscillations from spikes, where if the behavior lasts long enough to last for, say, Z cycles, then it's an oscillation. If it's fewer than Z cycles, then it's a spike. Just to give you a feel for how this expert system is structured, there's kind of a diagram down at the bottom here to show you how the data kind of shuffles through a sorting line, right? Where we check for different types of behavior, and then if the behavior is identified, then you can kind of imagine those segments of fuel pressure dropping into a bin that's, the fuel pressure has been classified as that type of behavior, and the rest of it gets shuttled off to be checked for other things. So we're checking for behaviors that we call type 1 through type 4. That's basically like, how high up is it spiking or oscillating? How far low is it? How long is it spiking up or down into varied degrees of severity? And then there's a number of points where we combine things that are, we're deduplicating things that were classified as different types of similar behavior that should not be, that are basically checking for the same thing in different ways. Or there's a number of instances where we could have a couple of different types of behavior happening at the same time. And so this kind of sorts through how all of that happens. Okay, to give you a sense of how this works in practice, we've got a couple of different examples to go through with our remaining time. So tanker A and receiver A, we start with raw data that we feed through the PELT change point detection algorithm and insert change points in the upper right. And then we apply the expert system, and we start being able to code these data segments as part of an overall type of behavior. And then in the bottom right, we're left with output that is relevant to the questions that the engineers have for test and evaluation, and we continue on with other types of analytics. To give you a closer look of what's actually happening, since we've been showing kind of an overly simplified demonstration, this is a graph of the same, roughly the same spot in a data stream as we've been showing previously. And we kind of break out all the different types of behaviors that could be happening either simultaneously, or if one's not happening, the other type is, you know what I mean? So we've got quite a list here in the upper right that's all color coded. Any kind of colored bars down below these red dotted lines are a different type of behavior that we care, either the engineers care about learning about and or the statisticians care about keeping track of. So we start off with steady state to the left on this plot, and then the data stream starts having transitory behavior, and we're classifying all the different bits and pieces in a fairly nuanced way here. Okay, this is another example, same taker, a different receiver. There's different forms of transitory behavior that we hadn't seen before, right? So the idea here is that this fact system is generalizable across tankers and receivers. So once again, we start with the raw data, we move to apply the Changepoint detection algorithm, and then the system expert AI, and the data stream goes on its merry way to continue to be analyzed. And here's again another form of data that we collect on tanker B with a third receiver that we hadn't seen before. It varies quite a bit. Okay, back to you, Michelle.
All right, so in general, this will allow us to have our classification become a lot more consistent, sensible, accurate, repeatable, knowing what settings we put things at. The same person, like engineer 1 and engineer 2, or statistician 1, statistician 2 can get the same answer for things. We'll get the exact same output if we run the same data with the same settings. So being able to figure out what are those settings for different receivers, for different tankers. In general, I think it is usually the tankers that have been dependent, changing any particular settings for things. But it will enable us to leverage all that time, effort, money, decision-making that we've needed to do this manually to instead use it on future projects. So it also frees up the SMEs and engineers to do additional work. So because things are subjective to how we were trained, what kind of experience do you have, often they have to duplicate that work because one person will look at it and be like, "Yeah, I don't know about this." And then they have to discuss it sometimes at length to figure out, well, what is it really supposed to be? And sometimes they will disagree with each other about what they think that classification should be. And so by including them in this process iteratively to get their feedback every time we find something new, did this do it right? What kind of behavior is this? Can we account for it? Can we add in a new part of the rule, et cetera? So that frees them up. Okay, we've already made a lot of these decisions. We can do spot checks for things versus having to more at depth discuss them. So this will save, we estimate, about 210 man hours per data package. So originally, I think we quoted about roughly 280. So going from 280, taking away 210 hours of that, that's pretty significant time saving. So it will also save a pretty significant amount of money. So there's always funding issues for everything. But to be able to go back and to do all of these things without breaking the bank is going to be pretty significant. So basically, we're making the impossible possible for us. So this is going to be a really significant change in a lot of our workflow that we're able to accomplish at the CTS. So in general, we've also got some future work lined up. So we need to, so now that we've built this out, we've tested it on multiple tankers, multiple receivers. We're about to start beginning the actual implementation on it for like a full scale like data package. We're gonna pick a guinea pig and go with that. See how it goes from beginning to end. And then we're also going to be having our engineers code alongside us and make all of those decisions and compare how well is the tool doing compared to how well do our SMEs do with it. And where do we agree, where do we disagree? Why is the tool doing better than what the engineers are doing or not? And if not, can we fix it so that it does, so that we can iteratively go forward with it? And we'd also like to be able to identify conditions that lead to potentially undesirable fuel pressure behavior. So if we can identify things soon enough, fast enough, that could help so that we don't have any knock-it-offs, no returns to base, no broken equipment for things during tests. So there's the potential that in the future, maybe we could help with some safety things as well. So.
Thank you.